Welcome to finding the inverse Laplace transform. So the idea here is we want to manipulate our function f of x, capital F of x, until it's split into forms that are recognizable. Until it is split into forms that are recognizable in the table. The key for recognizing is to focus on the denominators. Oh, manipulate somehow lost some letters. So we want to manipulate, there we go, our capital F of S until it is split into forms that are recognizable in the table, and specifically the table on the right side of the table. We will want to focus on the denominators and get them as simplified as possible. So we will focus on the denominators. We will need to use partial fractions. Since none of those right-hand sides had anything that was factorable. So these are just some things to keep in mind. So first trick we're going to use is linearity of the inverse Laplace transform. So if we have want to take the inverse Laplace transform of C1 times F1 of t plus C2 times F2 of t, we can go ahead and split across the addition and pull the constants out front. So this is equal to C1 times the inverse Laplace transform of F1 of t plus C2 times the inverse Laplace transform of F2 of t. So this is a useful trick to have. We can split using, say, partial fractions as much as we want. And then, of course, we can multiply by scalars, pull out scalars however much we want to force the format we need. Partial fractions. The only things we want in the denominator are fully factored. So essentially, the denominators can only contain one real root. So the denominators should be prime factors. Or in other words, should not be factorable. Unless they take the form something like s minus a to a power, then that's fine. But we will still likely wind up using partial fractions. So even so, we will likely need partial fractions. When we do partial fractions, we'll split them up into all of the individual possible types of denominators, and pretty much all the denominators should be recognizable in one of the forms. So all linear and quadratic prime denominators should be recognizable. On the right side of the table. The other thing we will sometimes do is just split our fraction into two fractions, splitting the numerator. So the last trick we have partial fractions, we have linearity. We can split the numerator to match the desired form. So we want to focus on the denominator because that's the thing that we can't really change other than via partial fractions. Whereas the numerator, we can split the fraction across addition and subtraction in the numerator as much as we want. We can pull out scalars from the numerator. So that's what we'll want to be playing with. So let's go ahead and find the inverse Laplace transform of f of s is equal to 2s minus 12 as the numerator, all divided by, in the denominator, s minus 2 quantity squared plus 9. So note the denominator takes the form s minus lambda squared plus omega squared. I apologize, I need to update my screen. So the denominator takes the form s minus lambda squared plus omega squared, where lambda is equal to 2 and omega is equal to 3. Now, if we switch over to our table, we have a couple possible right-hand side functions with that denominator. Looking at our table, we have an s minus lambda over s minus lambda squared plus omega squared, which came from e to the lambda t cosine of omega t. And we also have an omega over s minus lambda squared plus omega squared, which came from e to the lambda t sine of omega t. So both of those will be useful in forcing our function into recognizable form. So again, we have two rows in our table where the denominator takes this form. And so essentially what we want to do is we want to split our numerator so it's a linear combination of s minus lambda and omega. So we need to split the numerator as a linear combination of s minus lambda, or in other words, s minus 2, and omega. which in this case was 3. So our numerator that we're working with is 2s minus 12. So we essentially want to write 2s minus 12 over, we had s minus 2 squared plus 3 squared as something times s minus 2 plus something times 3 all over s minus 2 squared plus 3 squared. So in this case, in order to have 2s, we need a to be equal to. So we are looking at 2s minus 12 is equal to 2 times s minus 2 plus b times 3, or 2s minus 12 is equal to 2s minus 4 plus b times 3. I need to give myself a little more space. This means that we have negative 8. Oops, sorry about that. We have negative 8 is equal to 3b, or b is equal to negative 8/3. So we get that our f of s is equal to, we have 2 times s minus 2 over s minus 2 squared plus 3 squared, then minus 8/3 times 3 over s minus 2 squared plus 3 squared. At this point, we have this in the format that we can recognize. So this first piece, s minus 2 over s minus 2 squared plus 3 squared, this is the Laplace transform of e to the 2t times cosine of 3t. The second piece, that 3 over s minus 2 squared plus 3 squared, this is our Laplace transform of e to the 2t times sine of 3t. And if we scroll up to our table, those were precisely our two forms, and they came from e to the lambda t cosine omega t and e to the lambda t sine of omega t. So when we go to take our inverse Laplace transform, we have that the inverse Laplace transform of capital F of s is 2 times e to the 2t cosine of 3t minus 8/3 times e to the 2t sine of 3t. Or if you recognize, if you know where the f of s came from, so in this case, we know that s minus 2 over s minus 2 squared plus 3 squared comes from taking the Laplace transform of e to the 2t cosine of 3t, and taking the inverse Laplace transform should just take us straight back to that e to the 2t cosine 3t. The scalar multiples come along for the ride due to linearity of the Laplace transform. So we'll go ahead and take a look at one more example. Let's look at f of s equals negative 2s plus 3 over s minus 4 times s plus 1. So in this case, s minus 4 times s plus 1, we have a product of factors. So the denominator is not prime, nor is it just a power. But even if it is, just if it's not prime, we need to run partial fractions. So we are looking at negative 2s plus 3 over s minus 4 times s plus 1. This we should be able to write as a over s minus 4 plus b over s plus 1. So what we get is negative 2s plus 3 should be equal to a times s plus 1 plus b times s minus 4. The trick here, plug in values of s that make one of those terms on the right disappear. So if we plug in s equals negative 1, then we would be looking at negative 2 times negative 1 plus 3 is equal to 0 plus b times negative 5. Negative 1 minus 4 is negative 5. So we have 2 plus 3 is 5 is equal to negative 5b. And we get that b must be equal to negative 1. Similarly, if we plug in s is equal to 4, that will make that b term disappear. We are looking at negative 2 times 4 plus 3. This should be equal to a times 5 and then plus 0 on the right. So negative 2 times 4 is negative 8 plus 3 is negative 5. This is equal to 5a. And again, we get that a is equal to negative 1. So just checking, negative s minus 1 minus s plus 4 does give us that numerator we were looking for. So we have then that our f of s, capital F of s, can just be written as negative 1 times 1 over s minus 4 minus 1 times 1 over s plus 1. Those were that was what we originally split as. So I wrote it in this form because 1 over s minus 4 and 1 over s plus 1 are recognizable Laplace transforms. If we take a look at our table, they're both simply 1 over s minus a cases, and so that comes from our e to the at. These both take the form one over s minus a. Our first case, a equals 4. Our second case, a is negative 1. So we know that the inverse Laplace transform of 1 over s minus a is just e to the at. So we have f of s is equal to negative 1 times the Laplace transform of e to the 4t minus 1 times the Laplace transform of e to the negative t. And we just get that the inverse Laplace transform of our f of s is negative e to the 4t minus e to the negative t. Again, if we can write that hand side, if we can write the right hand side in terms of a bunch of as a linear combination of Laplace transforms, the inverse Laplace transform becomes the linear combination of the things inside the Laplace transform. So this is how we can kind of manipulate the right hand side using partial fractions, splitting up the numerators so that we can force it into a format we recognize.